So let's turn our attention to a data type we haven't really looked at very much so far, namely the data type of characters, and associated with that the data type of strings. So characters are the symbols that we can type from our keyboard, for example. So these are the type of items which are manipulated with software like word processors. So it's an important part of computational software that people write. So the way that Haskell represents characters in a program is to put the symbol between single quotes. So you have single quote A or single quote percentage and so on. Now, as all of you know, actually a character is typically stored in some binary format in the memory. So there will be a table which tells us how to interpret a particular bit. So if we want to call this a character, then this represents the character Z, for example. So there is a table lookup which tells us how to treat a bit string, which is essentially an integer, and convert it into a number. Sorry, into a character. Okay? So there are various standards for this. So the old standard, which is very common, is called ASCII. A modern standard which allows more character sets, for example, in non-English and especially symbols in languages from, say, places like India or Asia, which is called Unicode. Right? So Unicode is a 2-byte character representation. ASCII is a 1-byte thing, but basically there is this table. So now you need a way to go backwards and forwards. So you need to find out the code of a character and you need to find out what a given code corresponds to. So these are the two functions that Haskell provides for that. It's called ORD and CHR. So ORD basically takes a number, right, and gives us a character, and CHR takes a number, and ORD takes a character and gives us a number. So ORD gives us the code for a character, and CHR gives us the character for a given number. So these are inverses. So if I take a character, take its number, and then convert the character back, I'll get the same character. Similarly, if I take a number, convert it to a character, and then extract its number, I will get back the same number. So if we want to use these functions in our Haskell code, they are not included by default. So you have to import a character module. So you have to use this statement at the top of your .hs file, import data.chr if you want to use ORD and car. So let's look at a function that one might want to write. So this is the function we mentioned as an example early on. So supposing we want to write a function that converts all lowercase letters to uppercase letters and doesn't do anything for non-letters. So it should keep numbers as numbers, punctuation marks as punctuation marks, but small a to small z will become capital A to capital Z. So one way to do this without using any information about how characters are represented is just to exploit the fact that there are only finitely many characters. Say, for instance, we are dealing with the English, or what is more properly the Roman alphabet. It has only 26 letters A to Z. So then we can just write out 26 patterns. Okay, so these are now my 26 patterns, capturing all the given inputs that need to be mapped. And finally, we have something which will just copy the input to the output if it doesn't match any of these patterns. Right? So if I feed it a character which is not A to Z, then it will just return it. So percent will come back as percent, question mark as question mark, 9 as 9, but small a will become capital E. So this of course is a very brute force thing, and it relies on the fact that we can enumerate it. Of course, this is a very tedious way to write such a program. So what we can do is use the fact that in any of the encodings that Haskell systems will use, the letters are actually in blocks. So the small letters, capital A to small a to small z, will all occur consecutively in the table. So will capital A to capital Z. So will 0 to 9. Right? So for instance, if I have the overall set of encodings, then maybe I have one block which is small a to small z. Maybe I have another block which is capital A to capital Z. And now the crucial thing is that the distance from small a to capital A is the same as the distance from small z to capital Z. So if I look at the encodings, they are the same distance apart. So there is an offset. Right? So what we can do is now we can write this function which says that if now, because the the encodings characters can be compared. Small a is less than small b is less than small c and so on. So the given character lies between small a and small z. If ch is bigger than or equal to small a and smaller than or equal to small z, then we add to its code, this is the offset. Okay, so we add to the code of the given character the offset which will shift it from this block to this block, right, by a uniform amount. Wherever it is, it will shift by the same amount. And then we recompute the character back and we get the capital. Right? So small a will go to capital A and then we recompute using the CHR function. So this is a way of capitalizing using CHR ORD and the additional property that the ORD numbering for characters are actually consecutive. So usually programs that manipulate characters don't manipulate individual characters, but they manipulate strings. So a string is just a sequence of characters, right? So when we have a text processor or something like that, it will read a line of input, which will be a sequence of characters or even many lines of input, and it will do something to them. So in Haskell, the word string with a capital S is a data type, but it is only a synonym. It is exactly the same in every context as list of Char. So in other words, I can write strings using the familiar double quote notation. Right? So I can write a sequence of symbols with double quotes. So this is a string as you would see it in any other programming language. But internally, as far as Haskell is concerned, this notation is identical to having a list with 5 elements, each of which is an individual character. Okay? So this is basically how Haskell works. So therefore, the empty string, which is just 2 consecutive double quotes, is the same as the empty list. If I say double quote equal to square bracket open square bracket close, the answer will be true. Right? So this is just an alternative notation, what sometimes programming language people call syntactic sugar. Okay, so this is just a different way of writing the same thing, which is more convenient for the programmer. Now the useful thing is that because these are all lists, everything that one can do with lists directly applies to strings. We don't need separate functions for strings because we can take length of a string, because length of a string is just the length of the underlying list. We can reverse a string because we're just reversing the underlying list, and so on. So all the things that we saw for lists like head, tail, take, drop, all these functions work as well on strings as they do on regular lists. So similarly, if one write a function on a string, one would think of it as a list and use induction on the string and then talk about the function on the empty string as the base case and what to do if you have a string extended by 1 letter to the left. So here is a simple function. We want to check if a given character occurs in a given string. So occurs is a function which takes as input a character, a string to search for the character, and returns whether or not the character is there. So the base case says that if I have a character and I search in the empty string, then it's not there, so the answer must be false. And now if I search in a non-empty string, I compare it to the first character. So if it is the first character, then I found it. If it is not the first character, I must search in the rest. So I continue my search by looking for occurs C of X's. So we are doing the familiar induction that we did for lists on the string. We are doing the base case for the empty string and the inductive case for the non-empty string. So it's exactly like programming a list. So here is another function. Supposing we want to take a string and convert every lowercase letter in that string to uppercase. Now we know how to convert one letter because we've already written this function capitalize. Okay? So again we can apply induction. We say that if we want to convert the empty string to uppercase, then nothing happens. We just get back the empty string. And now if we have a non-empty string, what we do is we change the first letter to uppercase and then inductively do the rest. So we capitalize the first letter and then we apply 2 uppercase to the rest. So this is actually a situation where I have, say, a string which consists of n characters, right? And each of these I'm going to now apply capitalize to get a new set of characters, which if they are not capitalizable, if their punctuation marks or numbers will be the same, otherwise they will be the capital thing. So what we are doing abstractly is we are taking a function f, okay, in this case the function f is capitalized, and we are applying it uniformly to a list so that we get a new list of the same length where I have instead of C0 f of 0, instead of C1 f of C1 and so on. Now this is a very important operation which we need to understand for lists, and we will definitely come back to this later, but this is a specific example of it where we have just inductively defined how to capitalize a string. So moving on to another example, supposing we want to find the first position of a character in a string. Remember that in any list, the positions of a list of length n are from 0 to n minus 1. Right? So if I take the length as n, then the valid positions are 0 to n minus 1. So any position which is outside this range is an invalid position. So we could, for example, treat n as the default answer if the string is not present. So either it should give us the first position in S where C occurs, or if there is no occurrence of C in S, it gives us the default value, which is the length which is outside. So this is beyond the last position. Right? So for example, if I take the string battle axe, then there are two occurrences of A, here and here, but because of our numbering scheme, this is 0, 1, 2, so on. So the number that we should return is 1 because position 1 is the first occurrence. On the other hand, the letter D does not occur in battle axe. The length of this string is 10. The positions are numbered 0 to 9. So I return a value of 10 saying it was not found. So how do we write position? It's quite a straightforward inductive function again. So we take a character, take a string and return an integer. So if it is not found, okay, if it is an empty string, it's definitely not found. Remember that the length of the empty string is 0, so I should return 0 by our specification, right? And this is correct because if it were a valid position 0, then they would have actually one element in the string. So it has no elements in the string, so there are no valid positions. So 0 is the first invalid position. And on the other hand, if I take a non-empty string as before, I check whether it is the first position. If it is the first position, then with respect to this string, it is 0. But if I have not found it, then I would have accumulated the positions I have skipped so far. So if I don't find it, I add 1 to the position of the character in the remaining part. So if I find, for example, in battle axe, I would first check A with battle axe, okay, and I would say that this doesn't match. So it will be 1 plus the position of A in attle axe. And now it comes back with a 0. So I get 1 plus 0 is equal to 1, which is the correct answer. Okay. So one has to, the reason we are going through all these functions is to just get some practice in working with these inductive definitions on list strings, which are all basically different versions of the same thing. So as our final example using strings, let's look at something a little more complex. So supposing we want to count the number of words in a string. So we have to define what a word is. So a word by convention is a sequence of characters which doesn't have a blank space in it. So a blank space could be either a real blank. Okay, so this represents the blank character. This is a tab. Okay, so you can press the tab button on your keyboard and you will get some number of spaces depending on how the tabs are set. And this \n is a new line. So this is the familiar encoding that in any programming language, \t stands for tab, \n stands for new line. Okay, so these are white space characters. So we can first define a function which classifies a single character as a white space or not. So all it does is it for the three cases which we have defined white space, we might want to later on add cases, but right now we are only saying space, tab and new line are white space. Everything else is not white space, and notice that we don't need this value here, so we have this wildcard pattern which we mentioned last time, right? So if we don't require the input in the output, we can just ignore the name and just use this underscore as a wildcard pattern. So this says everything which is other than these three characters is not white space. So the first thing that we could do is assume that if I have word 1, word 2 and so on, then they will each be separated by white space. So I will have, in this case, 2 white spaces. So if I can count the number of white spaces, if I add 1, I should get the number of words. So the first attempt would be to just count the white space. So if I count the white space in the empty string, it is 0. If I count the white space in a non-empty string, then depending on whether the first is a white space or not, I add 1 or I just look at the rest. So if it is the first character, if C is a white space, then I add 1 and I continue inductively to count the remaining white spaces. Otherwise, I don't count this because it's not a white space and I just count the remaining things. So this is a very straightforward way to count the white spaces, but unfortunately, this would give us a wrong answer because in a function, in a thing like this where I have maybe 4 blanks between 2 words, it would say that there are 4 white spaces and therefore this constitutes 4 or 5 words when actually there are only 2 words. Right? So actually what is important is not the number of white spaces but how many times one goes from a word outside and back. So one could write a program to check whether we are inside a word or outside a word. If we are outside a word, so we have a word and then we have another word, right? So when we are outside a word, there may be many white spaces, but we don't care. Now when we hit a non-white space, we transfer to being inside a word. Now inside a word, we will ignore non-white space, but when we hit a white space, we will leave the word. Right? So we can use this idea to count words. So actually, it is enough to either check how many times we enter a word or how many times we leave a word. So in this case, we will count the number of times a new word starts. So a new word starts whenever you go from a white space, so from a space to say the character C, okay, or from a tab to the character X. So whenever we transfer from one position which has a white space to a position which doesn't have a white space, then by definition a new word starts. Right? So of course now if I have a sentence like the bat, okay, then I must make sure that I count this as the beginning of a word. So I must say that I go from a non-white space to white space, but I start directly with the letter T. So what I will do is I will always take whatever string I have and insert a space before, so the very first word gets counted correctly. So the word count, so this should be word count. So the function word count, which I'm going to write on a given string, we'll call this auxiliary function by first adding a blank space before the string. So now this makes sure that the very first word is counted correctly. Now we are fine. What this says is that if I have just a single character, then I can't make a transition. So I say there are no words. But if I have more than one character, see, notice that I will always call word count aux with a non-empty string, because even if this is empty, okay, this whole thing is the string containing one blank. So I will never call this the word C aux with an empty string. So I don't need a pattern match case for the empty string. So if I have one character, I will declare it as has no words. If it has 2 characters, because if I have only one character, okay, then it can't be a word. It can't be the starting point of a word because I would have flagged it at the character before. If I have 2 characters, I check whether the current character is white space and the next character is not white space. This is exactly this transition. Right? If so, I add 1 to the word count. Otherwise, I continue counting words as before. One important thing here to notice is that when we do the empty string, we said that the double quote is equal to, okay, this is an equality. However, double quote C is not in general equal to this, because when I write double quote C, this is the character C, whereas here this is a variable. Right? So when I write a function definition like this, I mean that this C stands for any character. If instead by mistake I had written double quote, it would say that this pattern matches precisely when I have a one element character C, a single C. Okay, so therefore one should be careful. In some situations you have to use the list notation even though you're dealing with strings. So to summarize, we have looked at the character data type, and what we have observed is that a string, which is the usual unit in which one consumes and manipulates characters, is just a sequence of characters, and hence Haskell provides the type string as a synonym for list of Char. And because it's a list, all the usual list functions can be applied to string, like length or reverse or take or drop and so on. And also because these are just lists, we can write functions that manipulate lists, manipulate strings using the structural induction exactly the same way that we use structural induction for lists, by looking at the base case, the empty string, and the inductive case a non-empty string where we separate out the first character and the rest.